that way. I thought it was a little mini lesson. I've never assigned this one before, but I saw it and I'm like, this is a pretty good exercise to get you prepped for the later design, the database modeling stuff. So, okay, so for this first one, how many records does the file contain? You just count the number of rows. I don't even know what the answer is because I haven't counted them yet. But so you got 1, 2, 3, 4, 5, 6, 7. I think it looks like. What if I miscounted? That's fine. But or if you did, but it's the number of records is the number of rows in a table. A row in a table is an instance of an entity. Is how I say it. I don't know if anybody else says it that way, but it's an individual manifestation of the entity type, right? Also known as a record. So, and then the columns correspond to attributes or fields or tuples. Well, a tuple actually, technically speaking, a tuple is all of this together. That's a tuple. All these fields combined in one record is a record is a tuple. My brain wants to call each individual thing a tuple, but that's not right. The whole thing's a tuple. And how many are there? How many fields? There's 1, 2, 3, 4, 5 fields. So should have got 7 and 5, I believe. But that's how you do. The important thing is you know how to do it. I think if you've watched the subsequent videos after this, then this is like really elementary, this question. But I did want to go over the answer explicitly, make sure we're all on the same page. Okay, this is where it ramps up a little bit. So what problem would you encounter if you wanted to produce a listing by city? How would you solve this problem by altering the file structure? So if you look at this table, let's say you just say, hey, I want to know just the names of everybody who lives in, what's a good one here? Florida. So excluding, well, let's do Tennessee because there are fewer in Tennessee. It doesn't matter which one you pick though. Actually, it says city, right? So, okay, let's say, let's say Gainesville because there's a couple of those. So I want to know everybody's name who's in Gainesville. As a human being, we can look at this small little table, right? And we look through the addresses, manager address. And I guess we're looking for the managers who live in Gainesville, but whatever. We want those names, right? So we would say, okay, Holly B. Parker is, and then Holly B. Parker again. Holly B. Parker. So this is like not a great example, but this is actually, later on we'll talk about, that's data redundancy too, so maybe that's going to be one of the further questions. But let me just answer the question. Now, what's the problem with listing by city? The problem is that each of the cities is stuck in the middle of a bunch of other, somewhat maybe even variant, not gibberish, but addresses. So you see how you have the road, comma Gainesville, comma Florida, and then the zip. You could have like 3334 Lee Road, Suite 42, or Apartment 7, or whatever. Again, it could the address format is going to be fairly regular, but it could vary, and you don't know where the cities start. You know it's comma separated. That's one way you could parse it. It looks like so far like you've got street, but let's say you had 3334 Lee Road, comma Suite 45, comma Gainesville. So it wouldn't be the same number of commas in that case. The whole point is you have to break down the manager address to get at the city, and that would take some scripting computing power. Like you'd have to write a little script to extract that city from the manager address. What would be better is that if in the design of this database table you wouldn't have the city in with the address. You would have a city column just by itself, and then Gainesville would be the only thing in that column. So in SQL, you do something like select project manager from managers, whatever the name of this table is, from managers where city, probably like Gainesville. You wouldn't say equals, you could say equals Gainesville, but you'd have a where clause that would say the city is basically this thing, and you would only have one value to look at. It would be an atomic value. You can't break the city down into a smaller thing than Gainesville. You'd have Gaines. What does that mean, right? So Gainesville is the smallest meaningful way to break that thing down. You want to strive to do that throughout a database for the most part. As far as like the manager phone, you could break it down, for instance, by area code and then the last 7 digits. Because area code gives you could search by area code to get like another geographic range, if that's something you're interested in. It's always possible using programming and scripting computing power to take these things and figure out a way to parse them fairly reliably, but it's a lot of extra work for something you could just do by making your database design simpler. So you want to have this in the back of your mind as always, like something to consider. For instance, also, and this is probably a further question, break down Holly and to break down first name, last name, maybe middle initial, maybe middle name. So break these fields down into smaller fields so you can more easily search by them, is the answer to that one. That was kind of a long answer for something sort of simple, but yeah, break this down into maybe street, city, state, and zip instead of just having one big, huge atomic block of address. All right, the next question. Okay, so this is just a continuation of the last question. If you want to produce a listing followed by last name, so you would just do what I said. You would break it down: first name, last name, area code, separate, city, state, zip, and so you would have more columns. You wouldn't just have, this would be divided into like how many? 1, 2, 3, 4. This would become 4 columns instead of just one big column. This would divide into 3 right here. First, middle, and last. And this would divide into 2. You would have area code. By the way, the dashes, I don't think you need to store those in a database. They're unneeded characters, because if you need it to be visually appealing to the end user, you would take the 10 digits, or maybe, the 3 for the area code plus the 7 digits, and you would fill those dashes in at the top front end level. You wouldn't worry, like you would have web page design, for instance. If this is a web page accessing a database, that would say this is the phone number, so you need to break, at that point you would break it down and insert dashes or parentheses or dots. I like using dots in phone numbers sometimes. It depends on what your style is and what your purpose is, but you would just store either the area code is 3 digits and plus the 7 digits is a separate part, or just all 10 digits. I mean, if you need to know the area code, that's part of the business rules, right? We sometimes do something in this business by area code. If you're unsure if you ever will, then maybe it's smart to break it down to area code. If you know you're never going to care about the area code, then just store 10 digits in a row for the phone number. But that's a design choice you have to make when it's time to create the database. Okay, this question gets into more of the hairy stuff that relational databases are really good at. So redundancies and anomalies. Redundancies are like the main, I'm going to say, probably not the only cause of anomalies, but they're the main thing that will cause anomalies in a database design. And relational databases are specifically intended to reduce these. So the redundancies here, notice, for project 21-57, Holly B. Parker. For project 25-9T, Holly Parker. So Holly Parker appears many times in this, and it looks like George Dortz appears a couple times, and the other ones don't so much that I can see. But the repetition of Holly Parker, that can be eliminated in a good relational database design, and we'll see how later. I think I talked about in the video a little bit. I don't want to go into detail because we're not there yet, but you just need to know that it is something we will do. It's accomplished through something called decomposition. Stop! My alarm's going off. I'm usually not awake at this point. Oh, that reminds me. Yeah, I have a doctor's appointment. This is TMI. You don't need to know this, but I'll have to start getting ready soon. But I can probably finish this. So, what are the anomalies? So, one anomaly is, let's say, the delete anomaly. What's it called? Deletion anomaly. So, let's just assume that we want data about all of these people in our database system. We want to retain Holly B. Parker, somebody, she's a project manager for different projects, and we need her details. For instance, we need her phone number and her address. So we need to make sure we preserve that information. And this might kind of seem silly, like that would never happen, but let's just assume that it will, because it could happen depending on your circumstances. Let's say it's our policy that when a project's finished, we delete the record for the project. The main thing it looks like this is here is it's a database of projects, right? And all the information related projects. So who the manager is, what the phone number for the manager is, what the manager's address is for that project, and how much the bid was for that project. And it's really hard for me to resist talking about normalization and stuff here, which is what you will learn about before the end of the semester about how to fix these things. But right now we just have to see the problems that we need to fix before we figure out how to fix them. So what the problem is say we delete this project because it's done, and then we delete this one because it's done, and then we delete this one because it's done. What happens is that we delete the whole row. The whole row is the whole record, the whole tuple, everything to do with that instance of an entity. In this case, it's a project entity. We're getting rid of all the data about that entity instance. That record is being deleted. What happens if you delete those three is that you lose all your data about Holly B. Parker. You don't know her phone number anymore, and you don't know her address. Obviously, you're thinking, well, I'll work with her. I'll just ask her. Sure. But it's not in the database. That's the whole point. That's the deletion anomaly. Let's say, hey, you're looking at this record for this project, and somebody said, oh, didn't you know here Holly Parker's there? And she says, and she's looking at you, looking at the project record. It's 2157. Here's the details. Oh, there you are. And she's like, I got married, right? And here's my marriage license, whatever. And she shows evidence that, and I'm not trying to be misogynist, but it is like the typical conventional thing. So now my name is not Parker, it's Parker-Dortz, right? So you update her name right there on that project in that record. But what's happening when you do that is that she's still Holly B. Parker in this record and Holly B. Parker in this record. It wasn't updated. If you update once, you would really need to update all the occurrences, all the redundant places where her data is stored. You'd have to update all of those occurrences. That's the update anomaly. I think that's enough for now. Let's see, update, deletion. I'm trying to think of how the insert anomaly would be. I'm trying to remember what the problem is on an insert anomaly. But one of the things is you would have to you'd have to have all the data on hand to enter something, and you would enter it again. Aside from that, it also takes up space. Right? Why are you taking up this space 3 times when ideally you could store her name somewhere in one place? When you update it, when she gets married or divorced or whatever, in that one place, changes her name. Let's just say she changes her name on a whim. We don't have to have a context for it. Then you only have to update it in one place. If you delete the project and it's not stored right, her name's not stored in that project data, you're not risking losing her name or her phone number or whatever. Maybe she gets a new phone. That would have been a better example, really. And so we would have to avoid any kind of ideological stuff. She updates her phone number changes. You have to change it all the places where it occurs. That's and of course computers can do stuff like this, but it's a lot of extra effort, and you're always risking every time you store data in multiple places, you're risking it getting out of sync with itself. So her phone number's changed in one place, but not the other. It's a lot more extra work to make sure all that data is consistent. All those data are consistent if you want to use the plural for data, like you're supposed to, or whatever. So that would be a redundancy. Anything else? Yeah, it's mainly if you just look at those. Yeah. So I covered everything I think I need to on that one. Okay, so this is just more of the same, right? You got the project name in here 3 times. Why are you doing it 3 times? And if you change the project name, you have to change it in 3 places. What else have we got here? The job code changes. You would have to change it everywhere. Let's see, what else have we got? if you there's deletion anomalies. Yeah, so job code, let's look at this one too. Job code's actually interesting. Notice that the job code and the job charge per hour, EE is 85, EE is 85, EE is 85, EE is 85, EE is 85. We haven't seen the business rule for this, but we can sort of fairly reliably be confident that we can infer from what we see in the data that there's a relationship between the job code and the how much you charge per hour. For a CT job, it's 60. For is that the only two? EE, CT. That looks like a BE down there, but it's EE, isn't it? Oh yeah, my eyes in this printout. I mean this screen. I don't know, but anyway. Oh, what's this? 26. Ah, so this one's 26. So we're not really even sure. And this was 62. We might not be sure from this if there's a relationship between the two. So the whole point is maybe these are wrong because of update anomaly. So maybe the charge changed for that job. Ideally, what you'd have is a job table. And if there is a relationship, if the job code E is always a certain price, then you would, when that price changes, you would change it in that table. I'm getting towards the solutions now instead of just the problems. But let's say there is a relationship between EE and the charge per hour. Then if the charge per hour changes to 90, you would have to change it in all these places. So again, it's an update anomaly. If you delete all the places where John D. Newson is, then he would be deleted. You would lose all the data about him in the whole database. And if you changed his phone number here but not here, it would be wherever the other one is. It would not be consistent between. So it's the same kind of problems as you had before. There's something I want to check. Yeah, okay. I think I covered everything here. Again, you can't tell from this. I mean, you would actually have to know the business rules, but this again, saying the different charges, is that because this charge code, this job code doesn't have a consistent hourly rate, or is there something that even if there's a reason that this does not always jive with this figure, you would need some kind of explanation for why. You would want to have a reason in your database why maybe there's a discount rate or something that you can apply that depending on the deal that you make with in your contract. Who knows? But one thing's for sure, you should probably have a project table, a job table, and an employee table, at least from what I'm looking at here. There's sort of hints about this in the names, proj underscore, imp underscore, job underscore. That tells you that there are probably different entities involved here. This should be broken down to at least 3 different tables. And we'll see more about how that works in the future. Okay, this is just a repetition of questions 1 and 2 with different data. So what would you want to do? Maybe break down area code and, the area code, then plus the last 7 digits of the phone number. Make that 2 different columns instead of 1. And of course, you want to break down the employee name probably as well. Anything else? And it doesn't say it here, but again, I would get rid of the dashes. Don't store dashes for a phone number in your database. Make that a cosmetic thing at the top level. All you need to know is phone numbers in America anyway are 10 digits always. So that's all you need to know. And even if you do break it down to area code and the rest of the phone number, which I think over time is because of the way cell phone numbers migrate around and most people have cell phones, area code's becoming more and more meaningless. So I'm not sure about the necessity of having a separate area code anymore. But even if you do that, you don't need dashes anywhere in the phone number. You don't store dashes. Same with social security number. Don't store the dashes. I mean, that's for human readability. It's for chunking. It's a psychological, it's a cognitive thing that helps us remember things. You chunk them into smaller parts, memorize the smaller parts, and then you can, once you've done that, you can memorize those. You know what chunking is, I think, intuitively, even if you've never heard the term. Those dashes are for chunking for human beings. It's not for the computer to process. So you can chunk it at the highest level, not at the back end. You want to do that at the front end. All right, so this question was kind of vague for me because I haven't looked at the chapter in a while. It's probably clear from the reading what they mean by data sources, but in case they weren't, they're really just saying, where do you think this data came from? Where, how was this data found and put in this? So you're going to have like project records somewhere. You're going to have employee records, and it looks like you're going to have job records. So it looks like to me, it looks like somewhere there's some records that tell you what the project number is and the name of that project. So project number 1 is Hurricane. Somewhere else you got employee records. So you've got employee number 101 is John D. Newsom. And then somewhere else you've got a job record. So job EE is 85 per hour. We're not sure about CT. So even if there are variant amounts of charge per hour for the job code, that's going to be in some job like file like that describes how jobs codes and charges work. And then like because it was kind of separated in columns, I didn't see this, but you're going to have an employee file where 101 is John D. Newsom and his phone number is 653-243-3245. And for the project number 1 is Hurricane, and they're 13 point. Well, actually no. That's something that's an even weirder thing. So the hours probably depend on the person working. So that's a combo thing that we have to deal with later. So it looks like John D. Newsom worked 13 hours on that job. David Schwann worked 16.2, and Ann Ramoris worked 14.3. So that's going to be some combination of the project and the employee, not just in the employee table and not just in the project table or files. Let's just say files because we're not talking about tables necessarily yet. So let me tell you the reason why this is in here. This is in here to make you start looking at the fact that you need to decompose all this data in this one big huge file. This is like, again, this is probably like called the projects file or the project details, the project work audit or job audit or charges audit. Who knows what they call it. But what it's supposed to give you a sense of what you need to do. You need to break these things up and separate them. You need to have just a project file, a table. And I'm going to say table now because that's the solution. You'll create a project table. You'll create an employee table. You'll create a job table. And you'll probably have another table, that my favorite table, right? Tell me what it is. It's the junction table between the employee and the project, because a project can have many employees that work on it, and an employee can work on many projects. That's a many-to-many relationship. So you'll have a junction table that will have the primary key of the employee, the primary key of the employee, primary key of the project, and then it'll probably have like how many hours separate, plus the job the employee did. And it would be a key to the job table, and you can look up how much charge is there. So this is how you would break this down. So for number 8, rewind a little bit and listen to number 7, because I kind of went into 8 and describing 7. You would need to break this down into different, it says files. Files, because we're not talking about tables yet in chapter 1, but it's tables. So you'd have a project table, employee table, a job table, and then you would have the table in between the two that tells you how much you charge for that employee working that certain job on that project. All right. Okay, this is just another set of data where you apply the stuff you've already learned from the previous sets of data. So there's not really a whole lot more. There's not really anything I can think of that's different in nature. It's just a different instance of what we've been talking about. So, for example, if you'll notice the teacher, they did break down. I mean, that's a little different. They've done the breaking down that we've suggested before. So you've got the last name, the first name, and the initial. That's a good first step for making it more possible to elegantly process your data. So you can search by last name, or I don't know why you'd ever search by first name, but might be something you do. But what you'll notice I think, what's her name? Maria Cordoza. Look at Maria Cordoza. It's Maria L. Cordoza on the second row. And if you go down, it's Maria I. Cordoza. Oh, and I don't know what row that is, but it's fourth from the bottom. So the initials are inconsistent, assuming that's the same Maria Cordoza, which I think you can probably assume it is. By the way, what is this? This is it looks like a schedule for teachers. So what building and room they're going to be in at what times. That's just their schedule, right? So the inconsistency, you can see the result of storing the name in multiple places and when you don't need to. In other words, eventually you need to break this. That's probably the answer to the next question or two, is that you need to break this down as well. You should have like a building table, and the rooms might be in there. I'm not sure. I'd have to break it down and see, but you definitely should have a teacher table. And then the rooms, yeah, so I can see it. You should have a building table, you should have a room table, you should have a teacher table, and then you would have a bridge table between the room and the teacher. So the bridge would be like, for room 204, you could use that as a primary key, 204E plus the primary key for Horace Wilston? I can't read. That's all blurred together. Wilston. You might even have a day's timetable, actually, because it looks like you have a set category of days and times. So like that would just be a table that you have a primary key for, like, for instance, schedule number 1, schedules kind of thing. Number 1 would be Monday, Wednesday, Friday, 8 to 8:50. That would be number 1. So you would just put that foreign key in for Horace Wilston. So the primary key, I should draw this out and show it to you. I might do that. I'm not going to promise it, but the long and short of this is the only thing you had to answer on this. You don't have to see the solution, and I should probably not go into the solution too much. But what you need to see is that you can get anomalies when you have the same data repeated places when you don't really need to. So you really should just have a teacher's table, and each teacher's name should be in there once. And that avoids things like, of course, capital L and lowercase l and capital I are often confused when written down. And that's probably a reasonable explanation for the fact that Maria has two different initials for the middle. I've seen this in real life. You probably have too, right? Maybe not with L, but I've seen the wrong middle initial I'm like, I know this. I can see why they did that. As a matter of fact, this is a big tangent, but genealogy, I noticed one time. I was looking for my great grandfather. He's buried in Asbury Cemetery, and it said that the death was 86 years, but the math made more sense if it was 36. That my great grandfather died at 36, because I know my great grandmother married twice after him, and he wasn't in the picture after 1890 something. He was born in 1860 something. So I know they got divorced, or he died when he was in his 30s. And so 36 made sense if you think about it. A 3 and an 8 handwritten. I would need to see the original record, but this was a transcription. So stuff like that happens all the time. Now that's not a database because it was only in one place, right? But it's not a database problem. But you can see how the fact that those kinds of things happen and you have your data stored in multiple places means that you can get data that disagrees with itself. What is Maria's middle name? Who knows? It could be Inez or Lopez. I'm guessing from Maria and Cordoza. It'd be something. As a matter of fact, middle names, Spanish names, isn't it mother's maiden name plus father's name? I forget what the scheme is. It's not exactly the same. We just pick middle names willy-nilly in the Anglo world, right? But there's other systems that have a certain pattern. Regardless, you get the point. It's the same kind of issues as the others. It's just a different set of data. So this question points you directly at the deletion anomaly. If you delete building com, when they say delete building com, it's unclear what they mean. Do they just mean the com, KOM, from all those places in those columns? If they mean building com as in everything on that row, everything on that record. So wherever you see COM, you delete that row. Then what you lose is the fact that building 204E is in COM. You don't know where that building is anymore. And what else do you lose? Let's see. Cordoza is in a couple different buildings, isn't she? No, she's only in COM. Is she only in COM? She's only in COM. So you lose all your information about Maria and Hawkins and Williston. You lose all the data about those teachers, what their names are at least. I mean, okay, you lose their names. That's fine. I think you probably would lose. What else would you lose? I guess you would lose their schedules too, those particular schedules. So you wouldn't necessarily, I mean, you might assume that their names are stored somewhere else, but you would lose this. You wouldn't know them when they're in this room. You wouldn't know that they're in this room, that they're in this building, and you would not know what time class met. Because all the COM for Williston, it's Monday, Wednesday, Friday then, and then Williston also isn't, he's at a different building there, but so you wouldn't lose information. Let's see. It's only the time assignments in COM that you would lose, because Williston's actually in a different building. But you would lose Maria. You wouldn't know that she has this schedule in this room at this time. So, yeah, you don't want to delete the whole rows because you lose other information. It's the deletion anomaly is basically what the question's about. And this is the one I said you didn't have to do. So if you did it, that's fine. You could have made up something. Obviously, you can't get with your classmates, but just judging by the tuple, right? The column names, what can we figure out? Like if let's say you have a student ID, if you deleted every instance of that student, let's say that student quit, says I don't want to ever be associated with your school anymore. If that's the only place where that instructor's name was stored as with that student, you would lose that instructor, and you would lose maybe the instructor's class days in the room that instructor had. You know, obviously that instructor's probably going to have other students, but in theory, it's possible that if you delete one thing. The long and short of this whole assignment is that there's a bunch of stuff together in all these tables. I was going to go scroll up through them, but I can't because you have to click. In all these examples, there's all kinds of different entities crammed together into one table. So that's one of the most basic things that you learn in database design is that you can't. It's not ideal in a relational database anyway. Well, it's not ideal in any database to store all these things together because there's a lot of redundancy. They can interfere with each other. There's a lot to parse through. It's a better idea. The general solution to this, which a relational database model makes a lot of use of, is to break these things down into separate places and then link between them. And again, it's not called the relational database model because of the relationships, those links, but it is a feature that you link things through references so that you only have to store something once, and then you just make references to it. And that way, if something changes, the only thing that you need to do is change in that one location. Or if all the references, if that person quits or something, the organization, all you have to do is delete all the references. You don't have to delete the other data associated with those references. So you'll see it in time to come. The other thing to look for is there are rules about this breaking down. What you want to break it down in such a way that the things you break it down to are all associated with one entity and not more than one entity or part of one entity. And this is something we'll see. It's rules called normalization, normal forms, first, second, third are the main ones we'll address. And I'll describe how they work when we get to them. It's a little bit of it's a not an intuitive concept at first. The first time you see it. It takes a little bit of explanation, so I don't want to burden your brain with that more. But the main thing you want to get out of this assignment was to see the problems that cramming a bunch of data together can cause, the anomalies with updates and Deletions, updates and deletions are the main ones. There's other ones too. I mean, there's retrieval problems, like, or if you have like the address again, that first example with the city crammed in the middle of all that, you have to parse that out. So first breaking down things into smaller pieces inside the one table, and then breaking things down into more tables is the solution to make your data more consistent and to have fewer anomalies. So ends this lesson. And again, what I'm going to do is at the point when this is uploaded, I will already have graded it. If you have turned in anything that's somewhat reasonable, then I will give you full credit. The main thing is I wanted you to think about all this, be exposed to it. And then this feedback can serve as feedback for everybody, because I think if you do have specific questions that I didn't address in this feedback about this assignment, then send me an email or something and I'll get back to you. Okay, take care.